All right. Welcome everyone to the first TAP colloquium of the 2021 fall semester. We are very excited to be back both in virtual and in-person mode this semester. So I just wanted to remind everyone of what the schedule looks like. So we are very fortunate today to have our own former graduate student, Nicolas Garavito-Camargo, giving the kickoff talk. And in a moment, Demetrius is actually going to be presenting him with a prize. On October 11th, we have our first in-person talk with Jimmy Juno, another one from our own local new theory postdoctoral fellow, Shengcheng Ma, on November 8th. And then on November 22nd, we will have Darren Ragazine. We have a shortened schedule this semester because we weren't sure how much was going to be possible in person versus hybrid, but we are hoping to transition back to a more full schedule next semester. And before I turn it over to Demetrios, the only thing I will mention is that I know we are having trouble with some of our emails going to spam folders. So one, check your spam folders, and two, remind your friends and colleagues about upcoming TAP events to make sure that they've also received them. All right, with that, I will turn it over to Demetrios.
Thank you, Caitlin, and welcome from me to everybody for this year's and hopefully in-person TAP colloquium series. There's going to be a lot of wonderful things that we'll do in the TAP, assuming that this COVID issue is left behind us. And the thing that we're going to do today, I really wish we did it in person, because it is a tradition in the TAP that started in the early 90s, especially for the graduate students here. I would just like to introduce it a little bit. Every 2 years, we ask for nominations or submissions of one paper by a graduate student that works on a theoretical astrophysics project. And we usually get a number of really, really high quality papers that are being submitted. Little committees put together by faculty that are not related at all to the research of the graduate students who have submitted the paper. And then one paper, sometimes two, are being recognized as the ones that have one little bit of notch of being a little better than all the others, and get a little award to promote the particular research and the particular person. And this year, just like all other years, we've had a wonderful set of papers. Several of you in the audience have applied for this little award, and the committee almost unanimously picked Nico Garavito-Camargo as the recipient of this year's TAP Graduate Student Research Program Award. The thing that particularly impressed the committee, as they wrote to me, was the fact that not only was this a paper with significant depth and originality, but in the short amount of time that it was published, it had already made substantial impact in the field, as several people noted. And I think this was really, really remarkable, and we were very happy to say that. So if it was in person, I would have given you, Nico, a little plaque for you to have and put it on your wall. A nice check to do much better things than the plaque with, but all of those will have to be sent to you by mail. There will also be a little inscription on a number of places for posterity of your name. All the previous recipients have their names on the wall, I believe in LPL and in the physics departments. But in any case, many congratulations for a really wonderful paper. And thank you very much. And let's everybody congratulate Nico.
Thank you, Demetrius.
And part of this exercise is that we would ask you to, as you know, to present that paper or whatever you want to the TAP group. And I would like to ask Gurtina to introduce you now for your presentations. Many congratulations again.
It is my pleasure to introduce Dr. Nico Garavito-Camargo, who, as you know, recently defended his thesis here at U of A. So Nico is currently a Flatiron postdoctoral research fellow at the CCA, and where his research program is expanding his thesis work to all these new and exciting directions. And as Demetrius mentioned, with Nico's paper, and really his entire thesis has made just such a remarkable impact on the way we currently understand and are discussing and pursuing understanding the dynamical state of our Milky Way galaxy. And as he's going to just talk about in his talk, There are exciting implications of his work for testing predictions from cold dark matter theory using nearby probes. So Nico, please take it away.
Thank you very much, Bertina. So let me share my screen first. Here. Oops. Okay. Let me put this full screen. Right. So first of all, it's an honor to be back at Stewart. It's an honor to get this prize, and yeah, I'm very happy to see. And it's, I would love to be there in person, but this is what it is, right? So yeah, today I'm going to talk about implications of the ongoing interaction between the Milky Way and the Large Magellanic Cloud for the CDM paradigm. And what I'm going to talk about is basically that we are in a very exciting era. We have a multidimensional view of the Milky Way. What this means is that we have precise distances, velocities, and metallicities throughout the galaxy and its stellar halo. So those measurements, what will allow us will be to test CDM theory, cold dark matter theory, at galactic scales, something that cannot be done outside the local group, right? However, there is something that is missing and that I work in during my PhD thesis, which is what is the role of the interaction between the Milky Way and the LMC? And you can see here the LMC in this beautiful picture of Gaia. In this context, in this CDM kind of scenario, how that changed the picture that we can test CDM at these scales. So as I'm going to show today, it really provides new opportunities to learn about the nature of dark matter. And it provides solutions to current challenges to CDM, but also it provides some difficulties to understand dark matter. So to start, let me review the anatomy of the Milky Way as we know it today. We know that we live in a spiral galaxy, have a bar in the center, and we live close to the Perseus arm, roughly 8.3 kiloparsec from Sag A star. The mass of the disk, which contains all the spiral arms on the bar, is roughly 10 to the 10th solar masses. But we know that this is not the entire picture of the galaxy. We know that galaxies, the stellar counterpart, reside in a dark halo, which extends like almost 100 times the size of the disk, and is almost 100 times the mass of the disk. This is the Tarmar Halo. And I think that something that is very important is that we know about this is because we have dynamical evidence of its presence. And this is through the rotation curve. We see that the rotation curve doesn't stop at the edge of the disk, but it continues and it keeps even increasing. The rotation curve remains flat. And this is, this has been studied since the 50s, but with the work of Vera Rubin in the 70s, then now we know that this really put strong evidence that there is dark matter. And this really allowed that at the end of the 70s, we now have a picture that there is some missing matter that we cannot observe in the universe. And this comes from studying the dynamics of galaxies. So today, I would like to basically show what can we now do in the field of galaxy dynamics to say more about dark matter. Of course, the picture of what is dark matter has evolved in time, and now we have a more sophisticated picture of what is dark matter. We know that dark matter could be a particle, and in the scenario that we have now, which is cold dark matter, the candidate or the most likely candidate is a particle that is massive. And now we can do computer simulations since a couple of decades now ago of how galaxies form. So hopefully you can see here how the substructure, which are dark matter halos, so what you are seeing here is the density of dark matter halos, start to build upon time, and they grow in this hierarchical scenario in which smaller substructures, which are these subhalos, fall into bigger structures, and that's the way that they grow. Of course, depending on the nature of the dark matter particle, like if you have lighter particles, or if you have particles that can interact, the amount of substructure that you will see will change, right? And that's a proof that people are now trying to find, like, what is the amount of substructure that resides, for example, in the Milky Way galaxy, to compare to expectations in given giving theories of what we think dark matter is. But today, I would like to focus on what information is in the entire halo of, for example, a Milky Way-like galaxy, that the one that we are seeing here, not in the substructure, but how the entire halo, the entire distribution of dark matter can tell us something about that. We know that we have evidence that this is the process of how galaxies grow because we observe stellar halos in other galaxies and in our galaxy. A stellar halo, as I'm showing here in this beautiful image from NGC 474, is this remnant of stars, the remnant of stars that have been accreted in galaxies that have built this central galaxy. So these were stars that were part of another galaxy that fell down into this galaxy. This observing stellar halos is very important because the amount of mass in the stellar halos is very small. For example, in the Milky Way, we think that is 1% of the total mass of the Milky Way is in the stellar halo. But since the stellar halos are, at large distances from the center of the galaxy, they are really tracing the potential, the underlying potential of the galaxy at larger distances. And at those distances is where we know that there is a dark matter halo. So basically, if we can measure, with the properties of the stellar halo, so we have velocities, positions, metallicities of the stellar halo, we can start proving what is the dark matter distribution in the galaxy. So not only knowing that there is a dark matter halo, but start to measure important properties. For example, what is the mass of the dark matter halo? What is its structure? So what is the density profile? So this is like a unique proof that stellar halos provide to us. Now, why this is important in the Milky Way at this particular time? So what I'm showing you, so in the background, this is an embodied simulation of what we think that a stellar halo of the Milky Way galaxy will look like. And overlaid, so this is in blue, these are all the stars in the simulations. And then overlaid, you see, this is what, for example, Sloan has observed, right? So in the inner part, like roughly between 20 kpc, Sloan has provided a map of the stellar halo, and it has discovered many substructures in the stellar halo. However, it's predicted that with LSST, now we're gonna prove, until the edge of the galaxy. So basically, all this region here is gonna be available to us. And the important thing is that it's not only LSSTs, but we have many surveys that are right now even observing, like DESI, Gaia, HST, that are really give us this multidimensional view of the Milky Way. So we are going to have, as I said earlier, we have velocities, proper motions, metallicities. So we have this complete picture of the stellar halo. So now the question is what we can do with that, right? What can we say about dark matter in the Milky Way? One of the traditional methods to say something about, or like to measure the properties of dark matter, is using stellar streams. Stellar streams, as in this picture is shown, are the final stage of globular clusters that are orbiting around the Milky Way. So you can see this is a globular cluster orbiting a Milky Way-like galaxy. And you see that as it orbits, like the globular cluster, due to the tidal forces of the Milky Way, start to develop these tails. So at the end, when you observe a stellar stream, you will see this very thin path of stars in the sky, as you can see, like in the right panel, right? You see the globular cluster progenitor is in the middle, and you see the tails of the globular clusters that form the stellar stream. So this is very powerful because what we can do is, like, basically the stellar stream gives you not only a position in phase space, like velocity, but it gives you the orbit, because you can see here that the stars that are in the stellar stream follow the orbit that the stream has done around the galaxy. This means that if we have observations, positions, and velocities of these stars, we can rewind the movie, assuming a given dark matter halo, and try to fit the present day morphology of the stream. So I'm going to play this again. Like, we can play this. We can, okay, assuming a dark matter halo potential, we start evolving orbital globular cluster, and then at the end we can compare what are the properties of the stellar stream with what you observe. And then we can do that many times to constrain what is the underlying shape of the Tarmar Halo, because we know that the potential is coming mainly from the Tarmar Halo, and of course we can put a disk and a bulge of the galaxy, right? So this is a way really to recover the properties of the Tarmar Halo, and this has been done. Let me change. It has been done, but this assumes something very important, is that the galaxy has to be in dynamical equilibrium. This means that the potential doesn't have to be changing in times and scales shorter than the crossing time of the galaxy. The crossing time of the galaxy is the time that it takes for a star to go from one side of the galaxy to the other side of the galaxy. For the Milky Way, at distances beyond 50 kpc, so from 50 to 300 kpc, that time is roughly half to 2 gigayears. And then remember this time, because we're going to come back to this. So assuming that, using famous stellar streams, different kind of shapes of the Tarmar Halo of the Milky Way has been used to fit the data that we have. So what is more common is, for example, oblate or prolate halo. So this is an oblate halo like a pancake here. This is a prolate. Triaxial is something, a mixture of these two. And also, like, what is the direction to where is pointing the major axis of this ellipsoid? And what is the density profile? If it's NFW, which is, what comes from the, or we think that halos have this particular density profile, what is its concentration, what is its extent, etc. So this has been done, especially with the Sagittarius stream. So the Sagittarius stream is, this is the remnant, or like the tails of the dwarf spheroidal galaxy that is here. And then in this picture, you can see this is the disk of the Milky Way. You can see the Large Magellanic Cloud and the Small Magellanic Cloud here. The Sagittarius dwarf galaxy is here, a little bit in the southern hemisphere. And then in Sloan, so this is the north and the southern hemisphere, observed by Sloan. And then you can see this overdensity of the stars here. The colors mean the distance, so you can see that there is like a coherent structure there. And actually, what is observed is like several passages, several arms of a star that belong to Sagittarius that are now in the stellar halo, and there are distances between 20 to 200 kiloparsecs. So this means that the stream from the Sagittarius dwarf galaxy can prove in this range of distances between 20 to 200 kpc can basically give us information about what is the shape of the halo. And this has been done, and until last year, actually, these were more or less the results of the community. And by the way, you can see in the kind of cartoon how it's more or less wrapped Sagittarius around the galaxy. So it's a very extended structure, which is everywhere in the sky in the stellar halo. So just looking at the stream morphology, he said, some studies suggested, okay, the halo is oblate. And then when you include the line of sight velocities, some students say, look, no, maybe it's prolate. And then the model that until last year was like, that we think like, it's the most consistent with all the observations that we have, said that it was triaxial, but with the major axis pointing perpendicular to the disk of the galaxy, which was kind of odd, because in that configuration, the disk will not be as stable as it is. So you can see that it was a very hard problem, and basically there was not a consensus saying, what is the shape of the halo. Okay, so this was until last year, but something that has been ignored so far is what is the effect of the Large Magellanic Cloud. So you have this beautiful picture from Chile of the clouds, right? So this is the Large Magellanic Cloud is the most massive satellite galaxy of the Milky Way. And in this kind of projection, in this beautiful movie from, figure from Gaia, we can see the Large Magellanic Cloud here, and its mass is roughly 10 to 20% the mass of the Milky Way. So it's a huge contribution of mass that is coming here. It's at 50 kiloparsecs, so it's inside the stellar halo of the Milky Way. So such a massive satellite coming for the first time in this kind of orbit that I'm illustrating with this line should be perturbing the halo, right? Like, I mean, this is not a minor merger. This is like an intermediate merger that should have some consequences in the halo, especially in the Tarmar Halo, because it's in the other parts of the galaxy. And in fact, using stellar streams, so this is again, well, now you recognize here Sagittarius here, but there are more streams, and this is in the slow and again like field of streams is called this image. There is a particular stream that is the Orphan stream, which is very faint here, but hopefully you can see it. The Orphan stream was also discovered to have, it's very long, so it's in this here is shown in the north, but also have is in the southern hemisphere. And with velocities from Gaia, now it was shown that, so now I'm gonna go to this map. So here you have in this axis, this is the like longitude along the stream. So this each point here are stars in the stream, and then the arrows illustrate what is the mean velocity of these stars in the stream. Now in equilibrium, the velocity should be aligned with the stream track, so they shouldn't be like perpendicular to the stream, right? This was 2018. This was a hint that there was something perturbing the stream, especially in the southern hemisphere. Not much in the northern, that you can see that here is more aligned, but in the southern hemisphere there was a strong disalignment. And then this was confirmed, like with the S5 survey, with the dark energy survey. They're looking at many streams, so each line here is a stream, and the purple, so it's the track of the stream more or less, and the arrow here is the direction of the velocity, the mean direction velocity of the stream. So you can see that there is a huge disalignment in most of them, even in some that you think that there is not. Like for example in Elky, the misalignment is in the plane, so we cannot see it here, but it's actually not aligned with the stream. So all of this was consistent with the picture that is actually perturbations that come from the Large Magellanic Cloud. So we now have this observational evidence that the LMC is a strong perturbation in the stellar halo, in the streams, and in the Tarmar Halo, right? So now we can come back to this question, like, is the assumption of equilibrium still valid in the presence of the LMC? Because if the LMC is coming in an orbit that is 2 years, so this is comparable with the crossing time that we saw that is for the Milky Way at those distances. So can we recover the potential of the galaxy in presence of the LMC? That's the question. And we need to understand how the mass is now being redistributed in this kind of scenario if we want to understand what is the shape of the halo. So this was the motivation to do these simulations that I'm presenting now. These are high resolution simulations, and in our field this means that these are like 100 million particles. And so we have several kind of LMC mass models. We have different Milky Way models with different kinematics for the halo, but we assume a spherical halo for the Milky Way and for the LMC before infall. And then we let evolve this to the present time. And something that was important for these simulations is to really reproduce the present day position and velocity of the LMC that we observe. If we want to make some predictions about the LMC, we really need to have like a very realistic orbit of the LMC, which is something that cannot be find like in cosmological simulations, right? It's really hard to find like the exact orbit that we think that the LMC is having around the Milky Way. So this is what we did. And this leads us now to the first part and what we found. And I'm going to talk here now about the dynamical friction wake of the LMC. So when you have a satellite galaxy coming, you will see that the satellite will decay over time, right? Why is decaying over time? If you don't, if we don't have dark matter, the galaxy will continue there. There is nothing that will make the satellite to lose energy and eventually decay. But since we have a dark matter halo, what happens is that the dark matter halo reacts, and this is what is shown in blue here. So these are overdensities in the Milky Way dark matter halo that have been enhanced by the passage of the LMC. And this has been predicted like almost like 80 years by Chandrasekhar, and he calls this the dynamical friction, which is basically that you have a sea of dark matters represented here with yellow dots, and you have a satellite galaxy represented with this gray circle here, moving in this direction with velocity. As the satellite moves through the sea of dark matter particles, the particles are going to be attracted to the satellite and will create an overdensity behind the satellite. So this will mimic like a wake from when the boats go in the sea, create a wake. So this is analogous. This is why this is called a wake. And eventually this will create a force that you can see FDF here on the satellite, that will decrease the angular momentum and energy of the satellite. That's why the satellite eventually decays, because have this overdensity behind. So this is how the satellite transfer energy and angular momentum to the halo. So yeah, this was predicted by Chandrasekhar in 43. So we study where is the dark matter wake that the LMC is inducing in the Milky Way. No? It is predicted, but has never been observed. So where it is. So we make in our 2019 paper, we made predictions of at different distances. So what you're looking here is at 70 kiloparsec or 100 kiloparsec. What are the overdensities? And this is the overdensities shown with the color bar created by the wake. So you see several overdensities in red, but for now focus on these ones that are in the circles. This is the wake at those distances. So this is this conic kind of wake, but you are seeing like a cross section in the sky of where the wake is. So we made predictions of, okay, where is it? What is the strength? What are the kinematics? What are the velocities of the wake? And so here is like a representation of this in 3D. So we have the Milky Way here, have the LMC at 50 kiloparsec coming. And then in this sphere is where the stars were observed in a follow-up paper that were with observers to try to find the wake. And these colors now highlight the overdensities in the dark matter halo. So there are not LMC particles here, just dark matter. So you can see the wake clearly is, inside the red line, around the red line, which is, is the wake. In the north, in the other part, you see another overdensity. We're going to talk about this later. But yeah, for now, let's focus on the wake. So this is the wake. The LMC is now here. The disk is in the middle. So this was a press release that NASA did for our work. So what we did was, okay, let's find what are the stars in the stellar halo between 50 and 100. Let's remove the star from Sagittarius and make a map of what is the overdensity of the stellar halo. So in the right, you can see the simulations that I presented earlier. On the left, this is data from Gaia and the WISE telescopes. You can see clearly that behind the LMC, there are this big overdensity, and actually the amplitude of the overdensity is twice as predicted in the simulations. And you also have this kind of the overdensity in the north part. So this is evidence that the halo is reacting, and this really looks like a dark matter wake. And if it's confirmed, this will be like the first wake ever observed, and confirming Chandrasekhar predictions. Okay, so now what can we do with this? We have this dark matter wake observed. This is a proof that the halo is responding to the passage, and this has to be dark matter. Of course, we observe this in the stellar halo, but as I say, the stellar halo is tracing the potential of the dark matter. There are some questions now that how do we move forward, because there are some challenges to really interpret and characterize the wake. For example, if we have a substructure, because as you saw, the stellar halos have substructure remnants of other events of accretion. So depending on what kind of accretion you have, for example, early accretion, or you have like massive satellites, or recent accretion, or satellites in radial orbits, you'll have in this case different signatures, for example, in velocities. So here the color bar are showing you velocities. So you see that the stellar halo, could have a lot of substructure. And when we compare to, this is what we predicted for the LMC, so the question is, how can we're going to observe these velocity signatures in presence of substructure? So this is still in, areas of research, but we know at least that, the accretion events in the Milky Way are not going to be these cases, for example, of very massive satellites. I mean, we have the LMC, or very recent accretion. We know that the accretion has been more or less kind of, not very strong in the last 10 gigayears or so. So now we need to know, okay, how we can characterize the wake and its kinematic structure in presence of substructure. This is very active right now, research. And then the other part is, okay, we have a wake. What can we say about dark matter? And what I'm showing here, these are wakes. So these are again overdensities of dark matter. In this case, this is a wind tunnel kind of setup, and then you have a satellite. The satellite is moving in this direction toward there, and the different in these columns is the time. So this is This is before these panels on the right. And then the difference in the columns here, in the rows, sorry, is what is the velocity of the satellite. But in this case, the dark matter here is something that is called fuzzy dark matter. So here, the particles that we're talking about are very light particles, like bosons, as opposed to in cold dark matter that we have WIMPs, which are very massive particles. In this scenario, particles can have like a wave-like behavior. That's why you can see that the wave have like this kind of interference patterns. And depending on the speed, the morphology can change drastically. So we have, and this is actually the project from Hayden Foote, which is a student at Arizona that maybe you know. The idea is to model what are the wake in fuzzy dark matter of the LMC induces in the Milky Way halo. And if we can see signatures, if we can use either kinematic signatures or morphological signatures of what will be the wake in fuzzy dark matter as opposed to cold dark matter, and then we can observe such signatures in the stellar halo, then that could really tell us something about the nature of dark matter. So this is, I think that's why this paper got so much attention, because first it was observed the counterpart, and then it's opening like a new window of new science that we can do with the data that we have, and this is very exciting. So to summarize this part, wakes are a prediction of dark matter models. Like if we have dark matter, we have to have wakes. Of course, the shape of the wake will depend in the dark matter that you assume. So please stay tuned to Hayden's work. But also the challenge now is going to be also observational. We have ongoing and future surveys that are mapping now the stellar halo, and we need to really map the 3D structure of the wake if we want to compare to the simulations and to the models. And of course, this implies that we really need to understand what is the role of substructure or how can we deal with substructure to really map the underlying dark matter distribution of the wake. Okay, the second part now is there is something else going on in the evolution of the Milky Way and the LMC, and you can see that these are very simple simulations, overall, but there are so many information that we're learning from them. For example, one thing is that please follow that you have the black dot here. This is just to highlight that the Milky Way, which is this halo, is moving from the center. It's not static. Because the LMC is coming, the pericenter is at 50 kiloparsec. Not the entire halo is not moving at the same speed. The halo is lagging behind. This means that if we are observing the stellar halo in the outer parts from the inner parts, we will see a differential movement just because of this center of mass displacement. And this was not known before. Like this was just, people assume that we live in a rigid dark matter halo, and all the streams and everything was integrated in orbits that assume a static halo. So this is an important motion, which is called the reflex motion, is the kinematic signature of this, of what is going on here. Now, this then was also observed in last year. So on the right here, you'll see, this is also an image from Gaia. This is the LMC. The contours here highlight where is the direction of that motion of the inner halo with respect to the outer halo. Traced with different stellar halo tracers, with satellite galaxies, with the stars, with K-giants, with blue horizontal branch. And then we saw that, well, the author saw that the inner halo is moving with respect to the outer halo towards this direction, to a previous point in the history of the LMC's orbit, like here, which is consistent with observation. Like the LMC takes some time to move towards the Milky Way takes some time to move towards the LMC. It's lagging behind, right? And this is very important because basically this motion, this mainly happened like in the last giga-year or so. There is a displacement of 50 kiloparsec in the halo. So this means that the halo potential is changing in time. Then we can revisit this question. Is the assumption of equilibrium still valid? No, because the center of mass motion is happening, and it has to be taken into account when we integrate orbits and when we measure the halo shape. The halo is changing in time scale that is smaller than 2 giga-years, because the barycenter motion, this motion happens, moves 50 kiloparsec in the last gigayear. So this is really changing the potential of the galaxy. And now the question is, we need to understand how the mass is being redistributed. What is the Milky Way shape in the presence of the LMC? Does this question now make sense in this kind of scenario to measure the halo shape of the Milky Way? All right. Just to show this was a result also that came last year. I mentioned earlier that the Sagittarius stream, was really hard to find a fit to the properties of the stream. People get different results if they use velocities or if they use the morphology, and it was still not solved this. However, last year, a group in Cambridge, actually, they include the potential of the LMC, allow the Milky Way to respond to the LMC, and including this reflex motion, and not including the wake, by the way, just the reflex motion. And they found that, so here the data are these blue squares, and the lines are orbits that they give in the models in different potentials. The ones that are closer, like the green, purple, red, these are models that were run with the LMC and accounting from the effects from the LMC. The other two were models that they just or ignored the LMC or didn't allow all the entire response of the halo due to the LMC. And then you can see that for the first time, this is the best fit ever done to the Sagittarius stream. So this is again evidence that the LMC is perturbing the halo, and we really need to take into account its effect in all the modeling that we're doing in the outer halo of the Milky Way. So beyond 30 to 50 kpc, this really matters. The Milky Way halo is not a static sphere as we thought even 3 years ago. But why is halo shapes are important? Like, why we should care about measuring what is the halo shape in the first place? So in these figures, I'm showing this is a halo of a Milky Way-like galaxy. In the Aquarius simulation, this was a zoom simulation of a Milky Way-like galaxy. And then this is at different times, so don't worry about the details, but just what is important here is that, so the ellipsoid that you see here, this is the shape of the halo, and the green arrow here is what is the direction of the intermediate axis, one of the axes of these ellipsoids. You see that as a function of time, this really changes, like, it's even rotating and everything. So the consensus, what we understand now is that the shape of the halo really depends on what is the accretion. You see that here, for example, the halo is aligned with the filaments, with the dark matter filaments. So the idea that we have now is that halo shapes have some memory about what has been the accretion process of the galaxy. And this is important because then we can back up, how the galaxy have been formed over time, how many satellites have formed the Milky Way, and so on. And then we can compare that to the, to what cosmological simulation said, and see if this is consistent, and and compare. However, then we can revisit, okay, is this still valid in the presence of the LMC? Can we, the shape of the Milky Way halo is just telling us about previous events, or the memory of the halo has been erased because of the LMC just came in? So yeah, you can see on the right, you can see this is the Milky Way and the LMC. These are density contours of dark matter. You can see that the shape, even though that we're starting with something spherical, the shape is very distorted, right? Can we disentangle then what the effects that are happening in the Milky Way, so the reflex motion, the wake, versus the filamentary accretion that we know that the galaxy had to be undergone in the past? Can we recover that underlying triaxiality before the LMC came to access that information? And even if we remove the Milky Way, like the LMC particles, we still have a shape that looks distorted. And so how can we compare this to the triaxiality that was before the LMC came? So to understand this, the first thing that we notice is that traditional halo models like oblate, prolate are not working with this highly non-axisymmetric halo shape. So we cannot fit a prolate, an oblate, or a triaxial halo to these kind of morphologies. So we moved to something that is called basis function expansions, which is a way to describe density and potential by doing an expansion in its modes. So for example, have an oblate halo, you can say, okay, we can represent the oblate halo with a monopole, a quadrupole, an octopole, and so on. And then at the end, we really can record this, well, in this case, this is axisymmetric, but even non-axisymmetric structures can be represented in this kind of expansion. So at the end, all the important, all the dynamical information of the system is represented in what are the amplitudes of each of these modes. And I'm not going to go into details of how we compute these modes, but just keep in mind that this is a powerful way to characterize shape potential of Tarmar halos. And of course, we do this at the, at one snapshot of the simulation, but we can do this in many snapshots of the simulation and let the system evolve. And in that case, we will have like basically a characterization of the time-dependent potential of the halo. But for now, let's focus on the present day. So we do this, and what we then compare is what are the amplitude of these coefficients for the Milky Way, halo in presence of the LMC, and some expectations from triaxiality from accretion in filaments. So in the x-axis here, we have where the modes. So you have one is the dipole, quadrupole, octopole, and so on. And here, this is the amplitude of the modes. So for the Milky Way in presence of the LMC, these are the x's here, the crosses. For very triaxial halos, this is the purple, and extreme prolate and oblate halos is these ones. So clearly, like if the Milky Way has a previous, very prolate or oblate halo, we think that then this will still be noticeable because the amplitude of the modes of those halos are stronger. However, like for what we think the Milky Way is like, or what the accretion history has been for the Milky Way, coming from cosmological simulations. So that's the green stars here represent what is observed, for example, in illusory simulation in particular. You see that even some modes are similar in magnitude to what is induced by the LMC. So it's not that clear that we can really recover the triaxiality in the presence of the LMC. Another important thing is like look that all of these triaxial and oblate halos don't have these odd modes here, which is because these halos are not axisymmetric, so cannot really represent the entire shape of the halo. So our proposal is we should really move away from trying to fit ellipsoids to the Milky Way because they are not really capturing what is going on in the Milky Way. So in this case, so in the case of the wake, we have a new opportunity to study dark matter. In the case of the shape of the halo, we really think that measuring the underlying triaxiality of the halo will require some more effort. So it's going to be more challenging. We require to have some information about the time-dependent potential of the halo, which of course can be constrained using embodied simulation as we have done. So basically the parameter space now is going to be way bigger. So now it's going to be more challenging trying to measure the halo shape. But we are working on that. And the idea is when we have this time-dependent potential that capture really all the effects caused by the LMC, we can use it to integrate orbits of satellite galaxies, globular clusters, and so on. This is an example of a movie of, this is by Ekta Patel, and this is from last year, working a paper on orbit and on creating what are the orbits of the LMC and the Milky Way satellites. So you can see this is coming from the past to the present time, and so we are starting to record what are, now that we have precise measurements of the velocity and the position of the satellites, what are the orbits, where are they coming from, right? So I'm going to play this again. However, in this movie that I'm showing, the Milky Way halo is still rigid, and then we have a rigid LMC halo. So the distortion from the reflex motion and the wake are not taken into account, but these are going to be the new generation potential models. That's what we're working right now, is in and improving this potential so we can improve the orbit that we are recovering. And this is worth the effort because we have very precise data. So we also would like to have very precise models, to have the best orbits as we can. Why this is important? Why, again, orbits? Of course, we have the accretion history, how the galaxy has assembled over time, but it's important because we also compare the kinematics of the orbits of the Milky Way to the kinematics of the satellites of the Milky Way to the kinematics of satellites in cosmological simulations. And this will lead me to the last part of this presentation, which is the presence of the LMC provides any hints of the understanding or even the solution of the planes of satellite problem. So let me talk about the planes of satellite problem. So as I said, there are many tests that we can do about the cold dark matter model in the Milky Way and galactic scales. And one of those is really the so-called plane of satellites. What happened here is that, so here we have the Milky Way disk is in the middle, and the satellite galaxies are shown in these colors, in these symbols. The arrows are the velocities. You can see that many, especially the classical satellites and some others, are in this face-on view are kind of orbiting in this direction, right? Like clockwise direction here. And when we see this now edge on, so still the disk is here, it seems that this is like a plane, and it's a thin plane, like you see like the units here. It's like a thin plane, and this is very odd. Like in these accretion scenarios, in general in the universe, we don't see these co-rotation patterns in these planes around, the host galaxy. This is odd. So this has been claimed as the plane of satellite problems. Another way to see this is like if we plot what is the angular momentum of these satellites, the direction of the angular momentum should be aligned. And this is what is shown in this movie, in this image. Sorry, this is the location in the sky where the angular momentum of the satellites point to. So we see that they are mainly clustered around here, right? And some even are like in the opposite. So this sculpture in particular is like counter-rotating the plane of satellites. Maybe we can see it here. Yeah, this is a sculpture. You see that is rotating the opposite way, but it's in the plane. Okay. So by the way, the direction of the angular momentum is what it's called in the literature as the orbital poles. These are the orbital poles of these orbits. Something that is, that called our attention was the LMC is in this plane, and the SMC, and it was curious. We said, okay, we have done the simulations. We can study what are the orbital poles of the particles in our simulations. So on the left, we see this is the Milky Way in isolation. It should be random. You see a slight under density here. This is something related with the initial state of the Milky Way in the simulations. But the important part is that when we include the effect of the LMC, not the LMC particles, just these are Milky Way halo particles, the orbital poles are really clustered nearby what is observed in reality with the Milky Way satellites. You see kind of this Z kind of shape, not S, but Z pattern here, mainly clustered around here. So this start to tell us, okay, maybe really the LMC has a role in forming these planes, right? So if you recall, there are two things happening in the Milky Way. One is that there is this barycenter motion that the LMC is inducing in the Milky Way. The inner parts are moving with respect to the other parts of the halo. This means that the inner parts is offset, just in positions for now, is offset from the outer halo. Like the center of the outer halo could be this triangle, or this is where the inner part was, and it's offset from the inner part. So what happens if you are measuring orbital poles of particles in a reference frame that is offset from the outer halo? So we do that, and we do this toy experiment. This is just that. Like, let's shift the positions by amounts that that are where we think that is the displacement that is happening in the inner halo with respect to the outer halo, and plot the orbital poles. So this is shown in these columns, and then in these rows, in these columns. And in these rows, you have the velocities. If we do also a shift in velocity, we know that, and it's observed actually, we know what is the magnitude of the reflex motion, the motion of the inner halo with respect to the outer halo. When we combine these two motions, in positions and velocities, we start to see that in some cases we get clustering of orbital poles just by making these shifts. And is maximal when the motions, like the direction, the position, and velocity, are perpendicular, because this is basically mimicking a circular motion, right, of the inner halo with respect to the outer halo. So we got this clustering. And also the wake, of course, like the particles that are in the wake are following the satellite galaxy. So these particles are going to be also have this coherent motion behind the satellites, so are going to be also clustered. So at the end, we conclude in this paper, which is not in print, by the way, it was just accepted 2 days ago, that both the center of mass displacement in positional velocities plus the dynamical friction wake cause orbital pole clustering. Now, what is the future work to do in this is we have to perform orbit integrations in the time-dependent potential that we're building of really the actual satellites. So far, I just show dark matter particles. Now we need to prove that this actually happens also to the satellite galaxies. We can also look, and we're doing this too in collaboration with Gina Samuel in Austin, and is looking cosmological simulations in systems that have LMC analogs and see how sensitive is the clustering of orbital poles to specific orbits of LMC analogs in these simulations. Can we also see this in cosmological simulations? Maybe the problem arises because we are not comparing apples to apples, but the Milky Way with the LMCs in a specific dynamical state that, you know, is not correct to compare to the mean cosmological halos, right? So in this case, now the LMC is giving a solution to a problem that was posed to the cold dark matter paradigm, which is like the kinematics of the satellites is not common in the universe. And here we're explaining why it's not common, and it's because we're in the middle of a merger with a massive satellite galaxy. So with this, I would like to conclude. First, the stellar halo has information of the distribution of dark matter in the Milky Way, and this is building in this traditional work from the dynamics community, which is we can by measuring the motion of the star, we can really say what is the potential of the galaxy, where is the dark matter distributed in the galaxy, and we will have very precise multidimensional data that can help us really have a 3D dark matter distribution of the halo. The LMC is the main perturbator of the Milky Way halo and offers opportunities and challenges to understand the dark matter distribution. For example, if we can map the shape and kinematics of the dark matter wake, can we constrain the nature of dark matter with the LMC wake? So this is a very exciting field of study now. We will have the data soon, so we will see. Hopefully we can say something about dark matter in the Milky Way. The LMC is erasing the dark matter halo's memory, and it seems that it's complicating efforts to record the underlying triaxiality and hence the accretion history of the Milky Way in those early times where the Milky Way was formed. And finally, the LMC induced orbital pulse clustering of objects beyond 50 kiloparsec mainly. Like in the inner halo, we don't see that clustering. Yeah, so with this, I will take questions, and thanks for your time.
Thanks, Nico, on a very comprehensive talk. Some pretty cool stuff. I'll be looking for hands in the participant list. If anyone's got questions. So I'm wondering, Nico, if you can elaborate a little bit more on observational efforts that you're thinking about and directions to go with, you know, when you've actually got 60 phase space information, what's the most promising direction to go to next for finding the wake in particular?
Yeah. So for the wake, I think that, well, now we have now the morphology kind of in density. Let me go back. Oh, sorry, I'm going to move a lot. Yeah, maybe here. We have the density observed. I think that now we need to really try to measure this kinematic signature, which is basically this dipole pattern here around the wake, which is, you can think about it, these are flows of particles moving into the wake, right? Do we see also in the stellar halo? I think that the stars in the stellar halo should also be be moving in this direction. The challenge now is that there are not many stars in the outer halo. So I think that, you know, surveys like, of course, like the LSST survey and DESI is also, they're going to give us this velocity that will allow us to measure these kinematics now. Another thing that I think is important is really constraining from the observations what has been the displacement of the inner halo with respect to the outer halo. We have a measurement of the velocity, but we don't have a measurement of the inner versus the outer halo. And having that information will really help us to constrain more the interaction of the Milky Way and the LMC.
I've got a question from Ben.
Hi, Nico. Thanks for this very interesting talk. I was wondering about the alignment of the orbital poles of the satellites. And I was wondering if in the simulation you can look at something like the history of these alignments and how, and whether they're transitory or, you know, whether satellites kind of move in and out of being aligned. That is, if there's a general tendency for the satellites to be aligned, but sometimes some are and some are not, or if it's kind of like an attractor. Once they get aligned, they to the orbital plane of the LMC, they stay there.
Right. Okay, so we do study what is the kind of you know, lifetime of the clustering. And we saw that it forms really very close to the pericenter of the LMC. So when this reflex motion is also maximal, and it stays for at least 1 gigayear. The thing that our simulation ends, and until the simulation ended, like even in the future of, you know, where the LMC is, the clustering was still there.
Interesting.
So what I think is like, it's not that these satellites are, you know, moving towards, you know, like to this motion is really the inner halo moving with respect to the outer halo where the satellites are. So I think that it will last as long as the inner halo is moving around. Yeah, I think that's what we need, or like the way I think about it is like the satellites are not doing anything. It's we in the inner halo are moving around that. So as long as we move, then we will observe this clustering.
I guess once they are aligned, there's very little that would make them be misaligned, right? Unless you had unless there was some kind of outside torque.
Mm-hmm.
So it might take, you know, on the order of you know, the time for the LMC to get to pericenter for them to become aligned, but then they would probably stay for much longer than that.
Right.
It's kind of what it sounds like you're saying. Thank you.
Thank you.
All right, well, let's thank Nico again for starting off our TAP Colloquium series. Thanks so much. And congratulations again on the TAP Research Prize.
Thank you very much, everyone.
Thanks, Nico. That was really, really beautiful. The very best movie didn't play at high enough fidelity on my screen, but the rest of the images were just really stunning.
Oh, okay.
It's just, yeah, it was a pleasure to watch.
Oh, thank you, Caitlin.
Cool. Yeah, Nico, we can chat about stuff later, and great to see you as always.
Okay.
Really.
Okay. Have a good afternoon. Take care.
Thank you,
so
Nico.
much. Bye.
Bye-bye.